to MIPI DevCon 2020. Thanks for joining. We're glad to have you with us today. Feel free to engage with the presenters and attendees by using the engagement tools at the footer of your screen. Click Q&A to engage with presenters and group chat to communicate with the attendees. You can simply minimize or maximize each of these icons with one click. To see the agenda, sessions, and demos, click on the Call to Action icon. Enjoy the conference.
Hi everyone, I'm James Goel, Chair of the MIPI Technical Steering Group and a Vice Chair of the Display Working Group. Thank you for joining my MIPI DevCon 2020 virtual event. Today, I'm excited to talk about our new MIPI Automotive SerDes Solutions, or MAS family of specifications. This group of specifications is designed for automotive applications that use our new Automotive PHY we announced earlier this month. I'm going to talk about new automotive trends driving display architectures and how MAS can be used by engineers to solve difficult display bandwidth design challenges. Before I begin, I'd like to point out this deep diver symbol that you will see on specific slides. It indicates that I've provided extra information at the end of this presentation for you to review offline. Also note that the audio transcript will be included in the notes under each slide of the PDF version. It's no surprise that the interior displays for next generation vehicles are evolving quickly. 5 new industry trends: connectivity, over-the-air feature updates, electrification, autonomy, and car sharing are increasing the number, size, and resolution of automotive displays. Consumers have become used to excellent mobile and television display quality and expect the same from their cars. The net result is a massive increase in total automotive display bandwidth. The increase does not come for free and is constrained by tight functional safety, security, power, weight, and RF interference considerations. Automotive engineers need new display system solutions to address these difficult challenges. MAS is a family of enhanced MIPI specifications upgraded to provide end-to-end protocols built upon the foundation of the new MIPI Automotive PHY. MIPI Automotive SerDes Solutions combine A-PHY with enhanced low power, low EMI, DSI-2 display, and CSI-2 camera protocols. When used together, MAS provides an end-to-end solution capable of functional safety, security, data integrity across an automotive-grade serializer-deserializer. More details of MAS and automotive display compression will be available in 2 new white papers to be published in October. These 5 industry trends increase the total visual bandwidth, resulting in a corresponding increase in the number, size, and resolution of automotive displays. The first trend, connectivity, takes advantage of new 5G, vehicle-to-vehicle and vehicle-to-anything wireless communication standards to increase access to high bandwidth data streams for multimedia content like video, gaming, and new automotive applications. Right now, many people use their cars as mobile offices to provide the freedom and flexibility to work anywhere, and enhanced connectivity is becoming a requirement in modern cars. The second trend, over-the-air feature updates, leverages this new connectivity to allow vehicle manufacturers to offer software subscription services that update the capabilities of vehicles after they've been purchased. These new software features take advantage of the advanced display hardware by providing user customizable look and feel options for the car's interior to match the tastes and preferences of each driver or passenger. The third trend, electrification, is well underway as vehicles transition from fossil fuels to renewable energy sources. This trend requires vehicle displays to minimize power consumption while maintaining very low electromagnetic compatibility, EMC, with communication and electrical systems. The final two complementary trends, vehicle autonomy and car sharing, combine to ease the driving task to the point where autonomous vehicles enable car sharing as a service. People that share vehicles expect them to automatically switch to their personal display profiles to keep the interiors consistent from vehicle to vehicle. All trends clearly point to more, higher, larger displays. Automotive display architects must adapt their next generation designs to accommodate this rapid increase in demand for visual bandwidth, or face becoming uncompetitive as the automotive industry transitions. This illustration contains multiple displays that will be found in next generation vehicles. The driver instrument cluster display is larger, brighter, and higher resolution than current displays. It can be customized based on driver preference or upgraded with over-the-air features enabled by the trend for advanced connectivity. The center information display contains navigation information and can be upgraded over the air with new features and applications as the automotive industry evolves. Below is the lower control display. All vehicle controls are configured through this touch-sensitive display, allowing the driver to make the user experience as detailed or as simple as possible. The co-driver display allows the front passenger to customize their space, set their temperature controls, and watch their own content, including video, news, and gaming. The left and right side mirror displays are based on the next generation of exterior sensors, and more detail is provided on this application later in the presentation. On the right of this slide is an example table indicating the next generation of display sizes and resolutions taken from publicly available sources. Note how large these displays have become, along with an increase in display resolution compared to existing vehicles on the road today. The key takeaway is the obvious increase in total visual display bandwidth. Of course, these displays all need to meet stricter electromagnetic compatibility requirements to reduce interference for in-vehicle Wi-Fi and 5G wireless communications. There is also the need to reduce power to ensure the longest possible distance on a single battery charge, all while maintaining functional safety and data integrity. This slide shows rear screen displays that can be configured based on user profile and preferences. The rear view mirror has been replaced by a display connected to a rear camera. There are two important points illustrated on this slide. One, it's interesting to note the aerodynamic improvement in low-profile side sensors compared to traditional external mirrors. Displays are not necessarily close to an ECU mounted in the dashboard and often require longer cabling solutions to reach displays in the rear of the vehicle. Internal digital side view mirrors have a number of benefits over traditional external glass mirrors. One, as we saw earlier, the lower profile external sensors improve aerodynamic performance, reduced wind noise, and increase nighttime and poor weather visibility using advanced sensors and wide field of view optics. Two, internal mirror displays enable instant zooming and customizable driver display positioning that is unaffected by weather. And three, ADAS lane departure, blind spot, and backup assist symbology is also supported. We can divide these automotive display use cases into three separate categories. One, short distance inline dashboard displays. Two, long distance rear seat displays. And three, digital side and rear mirror displays using external sensors. All use cases feature support for multiple high resolution displays. 2. The dashboard displays are typically inline and only a short distance from the ECU, while rear displays and digital mirrors can require up to 15 meters of SerDes cable length as per the A5 specification. Each case, displays may need to support functional safety, security, EMC, and ultra-low packet error rates, especially if displays compression is required. The dashboard use case will be used to illustrate a daisy chain display topology, while the rear displays illustrate the hub and spoke system. I will go into detail for the daisy chain system in this main presentation, but the hub and spoke is covered in the deep dive section at the end. The digital mirrors are interesting because they must maintain pixel integrity from the camera sensor to the ECU to the side mirror display. This is where MAS excels. Its protocols provide end-to-end solutions with functional safety, security, and high data integrity. This slide introduces the MAS, or MIPI Automotive SerDes Solutions concept. MAS supports an end-to-end protocol chain with functional safety and security over the MIPI Automotive PHY. In this diagram, the camera produces CSI-2 data streams with new functional safety and security information added to the protocol as indicated by the shield and lock icons. The CSI-2 data is transmitted over A-PHY to an automotive ECU for data verification and signal processing. Once ready, the ECU generates DSI-2 packets with functional safety and security for transmission over A-PHY to the display. Please note that MAS optionally supports HDCP for protection of high-value content. This slide illustrates MAS applied to the digital side mirror application. The digital mirror display is a great application for MAS because it requires the camera sensor, ECU, and display to work together as an end-to-end system to ensure functional safety and pixel data integrity. There are 3 levels in this diagram. The top illustrates how the external side camera sensors capture pixel data and sends it to the MIPI A-PHY bridge chips using new CSI-2 functional safety and security protocols over a C-PHY or D-PHY physical connection. MAS specifications define the CSI-2 camera service extensions and protocol adaptation layer required to efficiently pack sensor pixels onto A-PHY data frames used for both A-PHY TX and RX bridges. The middle level illustrates how ECUs receive the pixel data from the camera and verify the information to ensure functional safety is correct before signal processing. Once the image has been evaluated with proper graphic symbology, it's overlaid. The display generator sends display pixels out using the traditional DSI-2 protocol with display service extensions and protocol adaptation layer specifications, defining efficient A-PHY data frame packing. It is important to note that MAS CSI-2 and DSI-2 functional safety and security specifications were designed to provide an end-to-end system solution that leverages A-PHY as the foundational serial deserializer. The lower level illustrates how the end-to-end display receives the A-PHY data frame from the RX bridge and displays the picture using legacy C-PHY or D-PHY physical connections. Some general comments. As mentioned earlier, the end-to-end functional safety and security are maintained by a series of MAS specifications designed to work together. The CSI-2 and DSI-2 protocols are not transcoded between the device and the A-PHY bridge. There are MIPI adaptation layer specifications that define how existing MIPI protocols are encapsulated for efficient A-PHY packet framing. MAS also supports GPIO and I2C, I3C adaptation layers for APHI to support existing CSI2 and DSI2 systems. The details of this will be described in future white papers and DevCon presentations on mass display details. This slide illustrates a mass daisy chain topology for the dashboard display application shown here. The ECU processor is embedded in the dashboard, and these displays are physically in line with each other as illustrated in the picture. Note, both digital side mirrors are at the end of the daisy chain, and this is done on purpose. This architecture scales from the lowest auto trim level that uses only the top 3 displays up to the highest trim level where co-driver displays and digital side mirrors are more popular. The application processor generates all display content and uses mass DSI-2 or VISA DisplayPort interfaces to connect an APHI bridge to the first display in the chain, which is this blue arrow. Mass supports a homogeneous and heterogeneous architecture with more details provided in the deep dive, along with an alternative hub and spoke architecture. Each subsequent display parses the required pixel stream and sends it on down to the next display in the chain. In this example, the left side mirror and right side mirror displays will require the least bandwidth because they are at the end of the chain. Mass APHI supports the high pixel bandwidth required by the blue arrow, and this is supported and explored in the next section. The first blue arrow connection shown in the previous slide contains all display content for the dashboard. The next section analyzes the display bandwidth requirements of 7 different dashboard display configurations and applies the optional VDC-M 6:1 visually lossless compression to study the corresponding improvements in bandwidth. The MIPI Display Working Group completed an expert study of VDC-M compression for automotive images, and the results are presented in part 2 of this DevCon presentation. More details are available in the deeper dive section. This table summarizes the pixel display bandwidth analysis for 7 different configurations. Each row calculates the display bandwidth requirements from the previous daisy chain example for a functional automotive trim level. Across the top of the table are the display parameters and then the total bandwidth required for all displays together. This is the amount that must be supported by the blue arrow in the previous diagram, because the first connection in the daisy chain must contain all displays together. The last set of columns indicate the number of PHIs required for the automotive APHI, DPHI, and CPHI bridge connections. Let's focus on the highlighted total display bandwidth section. The first 2 columns have different source pixel sizes. The source 24 bits means 8 bits per component, and the 30 bits per pixel means that 10 bits per component are used. The calculations highlighted in blue indicate the total uncompressed data rates for each of the 7 levels. These data rates can be reduced drastically using VDC-M compression. The compressed rates highlighted on this slide indicate a 6:1 reduction in bandwidth. This allows the design to reduce the number of PHI lanes indicated in the last 3 columns. In summary, the benefit of reduced bandwidth using VDC-M compression is a reduction in power, improved EMC, and cost through interface savings. VDC-M is a great technique when the compression quality meets the designer's goals to be visually the same as the original uncompressed image. This is called visually lossless quality. The next section of this presentation focuses on how MIPI evaluated the visual quality for example automotive images. The MIPI Display Working Group asked the question, is VDC-M 6:1 compression visually lossless for automotive style images? To answer this, We followed these steps. Step 1, MIPI created example automotive dashboard test images. These are available for MIPI members to download and evaluate. Step 2, we selected and used the internationally accepted 29170-2 standard protocol for testing high-quality compression. This is publicly available from the ISO website. Step 3, 7 visual quality experts followed the protocol and evaluated all automotive images. And finally, step 4, the results are summarized in a quality report and posted for members to review. More details will be published in the October white paper. The video on this slide illustrates the first static image testing protocol using an exaggerated compressed image. The subject looks at these 3 images and selects the image on the bottom that matches the reference quality on the top. This is done many times over all the images, with the bottom compressed image randomly positioned on the left or right. Over many trials, high-quality compressed images will have the same 50% chance of selection as the uncompressed version. In this animation, it is switching left and right much faster than a subject would normally do. This is for illustration only. The video on this slide illustrates the second dynamic flicker testing protocol using an exaggerated compressed test image. You can see the compressed test image is alternating with the original, and if the compressed image is different, it will become obvious to the tester which areas are not visually lossless. The idea is to make it easy to expose visual differences with the flicker testing. This is done over many trials with randomly positioned flickering on either the right or left side, exaggerated in this animation. Over these trials, high-quality compressed images will have the same 50% chance of selection as the uncompressed version. This slide contains 6 examples of the MIPI automotive test images commissioned for use in visual quality testing. These images also have day and night variants to simulate a change in contrast. Low-resolution versions of the complete image set are available in the deep dive section, but the high-resolution 4K versions must be downloaded from the MIPI website. This slide illustrates specific areas of interest we evaluated on various images. The shading background is covered in fine diagonal lines, and this detailed area should be preserved in the compressed image. We also evaluated the areas where text and graphics were close to fine details. Expert testing revealed that all areas of interest passed both static and dynamic evaluations. These summary of results come from gathering statistical results from 7 experts over multiple visual trials as described in the ISO quality standard. A full trial would require many more subjects to be statistically accurate. VDC-M 6:1 compression testing on these images was highly successful, but automotive design teams still needed to follow their own quality assessment protocols because the MIPI content will differ from their final production graphics. The study report is available from the MIPI executive for those interested in following up on the details. In summary, there are 5 new trends driving automotive displays to become larger, higher resolution, and more numerous. This results in a massive increase in visual bandwidth. Automotive display architects are challenged to meet a variety of complex use cases with existing SerDes solutions. MIPI introduced MAS, the MIPI Automotive SerDes Solutions family of automotive specifications built upon the APHI. MAS displays support daisy chain and hub and spoke topologies for the use cases discussed in this DevCon. MIPI DSI-2 display protocols support advanced VDC-M visually lossless compression, and the latest MIPI 6:1 compression study explored the quality possible on a variety of available automotive images. MAS provides excellent end-to-end support for functional safety and security display solutions. It is a great choice for next-generation automotive display architectures. Thank you.
Thanks, James. Encourage questions to come in through the Q&A panel. I do see that we have one here. There are already solutions on the market that work with high-resolution displays. Why is this architecture better than existing systems? Hi, James. I'm not quite sure, but we're unable to hear your audio. Perhaps you can unmute your line.
Oh, I'm sorry. Dervla, can you hear me now? That was my mistake.
Yes. Did you catch
Okay,
that
sorry
first
about
question?
that. I heard the question. Yeah,
Okay.
so to me, it boils down to functional safety, security, and cost. MAS has been reviewed by industry experts, and it's based on an industry standard set of specifications. You know, MIPI members can only make money from this if they can deliver on the functional safety and security of MAS at a reasonable market rate. So MAS-compliant products have to be compatible with each other to ensure that different vendors and products will interop, and that will drive the cost down. There are also public, compliance test specifications under development by expert test companies to help drive this. Existing market solutions are based normally on proprietary closed systems. And these systems require automotive manufacturers to commit to specific architectural solutions that may be difficult to audit for functional safety. So MAS is based on MIPI's 10-plus years of mature protocol specifications for, mobile, and they're expert in low power, low RF costs. MAS was designed specifically to work with legacy systems. The openness of MIPI ensures that, we're going to have broad industry support, drive down costs, increasing quality by allowing the market and competition to reduce risk.
Thanks, James. Next question coming in. What is the best way to evaluate visually lossless compression quality for my automotive architecture?
Sure. So I think the best way to evaluate compression quality, as I showed in the presentation, is really to break it down into a number of steps. The first steps I suggest is gathering all of the most challenging specific graphics, display content, rear sensor content, side view mirror content, and getting the team of graphics designers and other user experience specialists who will need to approve it, get them all into the same team, your visual quality analysis team, and they will give you all the inputs. Now, the next step will be to download the free VDC-M compression software tool and then run a series of compression tests to determine what the maximum savings you can achieve. So I recommend using the maximum 6:1 compression as we did with the MIPI study. And then finally, follow the quality assessment protocol I outlined in the presentation. The ISO 29170 has been carefully validated. There's extensive literature that validates this approach for low impairment compression. And that way, at the end, if your team accepts this maximum compression rate, you'll be using MAS to its fullest bandwidth capacity at the lowest implementation cost. Thanks.
Thanks, James. We're almost out of time. One more question that has just come in. The system is new and unproven on the market. How can I be certain my system will work?
This is related to the first question, really. It's really one of risk tolerance and the ability to adapt your design. What you want to do is use AFI in stages. MAS is designed to work with legacy systems, and what you can do is start with the core AFI bridges and then upgrade future automotive display architects display architectures as you move forward. And that way you can incrementally test the improvements from each layer and ensure that your system will work while meeting and using all of the latest MAS features. That's it, Dervla. Thank you.
Thanks very much, James. We are out of time. Thanks again, everyone, and suggest we move on over to the Teledyne LaCroix demo. Thanks again, James.
Great. Thank you, everyone. Take care and have a great year.